So we're really happy to have Matteo Marsili to give us a talk today. So Matteo is a researcher from ICTP, so International Center for Theoretical Physics in Trieste, Italy. And he was my postdoc advisor, so I'm really happy to have him here. And he has a broad interest in statistical physics and non-equilibrium statistical physics application to quantitative economics also in the past, system biology, neuroscience, and now he's going to talk about statistical inference also most importantly. And today he's going to talk about his latest interest, which is what is abstraction.
Yes. Okay, so thank you very much for coming. Thank you very much, Claudia and all the others for organizing this talk. And so what I'm going to do is to share with you some ideas that I've been developing over the recent, actually, maybe years, on abstractions, what is abstraction in very abstract terms. Okay, so I think this is a very timely topic because essentially we have reached a situation where we can create machines that have some intelligent behavior. Okay, so they do what we do. They abstract and extract knowledge, and so these things, these properties, these functions, these cognitive functions start to be. I mean, it is possible now to understand, to probe, to try to understand what these functions are from a quantitative and scientific point of view. Okay, and well, these are just two quotes to motivate what I mean, to show you what is my motivation is that really understanding cognitive functions is actually may help us understand what is really important about being human, okay, which is not intelligence, it's something else, no? Eventually, okay. Okay, so now abstraction is a fantastic topic. It has been studied, I think, since ever. But this is just a summary of what I learned about it recently. So the first important contribution is the one of David Marr, which says that we distinguishes three different levels of abstractions. So, and one is the conceptual level. So the fact that which is where essentially language is how concepts are represented inside how concepts are represented conceptually, essentially. And the other one is the algorithmic aspect of how this representation is achieved in an algorithmic manner. And the other one is how this algorithm is embodied in a physical device, okay, which may be the brain, right? And now, this is, of course, I mean, on the other side of that, I mean, the sensory apparatus, there is, there is a larger hierarchy on that side. In the end, leading to the real world, which is not abstract. But in some sense, you can see this axis of abstraction or conceptualization is moving away from reality, from physical reality, okay? And in the end, it's essentially bringing us to these capacities of writing poetry or all these kind of things. So there is another hierarchy which has been developed in neuroscience, which is a functional hierarchy of systems built into systems that essentially enable these functions to take place. I'm not going to enter into this. So what I will focus on is quite simple. Oh, sorry, this quite simple setting, which is essentially how abstraction emerges in a deep belief network. This is a very simple. This is a very simple system. It is a system that, however, is able of abstraction, in the sense that what people have found is that if you look at what the different layers of this machine do, they essentially represent more and more abstract features of the data as you go deep. Okay, so you have this notion that abstraction develops with depth. Okay, and the idea is that essentially what I'm going to do is to try to look inside here and to find search for signature of abstraction. So what does abstraction really mean in this simple system? Yeah.
Neural network, even becomes more deep.
Sorry?
If you have more layers in the neural network, that means it's more deep.
Yes. Yes, so, and what I'm going to do is also to focus on what is called unsupervised learning. Unsupervised learning means that I'm going to try to study a generative model, a model that internally generates a representation which is able to generate the data, essentially, or data that looks like the one with which it has been trained. Okay. Okay, so this is a little bit the path I would like to bring you through. So the first step is that abstraction is actually related to invariances, and is related to essentially getting rid of invariances, okay, from the data. The second step I want to try to convince you is that from the point of view of this network, if you are inside this network, then for you, invariances are exactly like noise. Okay? So you treat invariances like you treat noise. Of course, noise is not meaning, but the question is, how do you quantify meaning? And essentially, this will bring me to tell you about quantitative measure of relevance that we developed over the past few years. Okay, and the remarkable thing is that when you try to find a model that has a maximal relevance, that is maximally, that contains a representation which is maximally informative, then you find just one model. If you limit yourself to this simple setting of just binary variables, like in the DPM. So this is quite interesting, because then you have this model, which is we call the hierarchical feature model, that allows you to really ask these questions. okay, to ask the question of, because essentially the issue is that once you have a candidate for a model that is an abstract representation of knowledge, then you can really ask yourself question of what is learning, what is abstraction, etc., etc. So the first thing I will try to do is to distinguish between learning and abstraction and understanding. So understanding, learning is just finding a machine that is able to generate the data, like the one that has been trained. Understanding instead is like projecting the data into a representation that already exists. That is your way of organizing knowledge, but it's pre-existing. Okay. And then I will look at whether you go deep in a deep belief network, whether you get closer or not to this abstract model of say of a representation. Okay. Okay, so first thing is also do interrupt whenever you have questions. Probably there is no need to say this, but okay. So the first thing is abstraction has a lot to do with invariance. And essentially the idea is that the internal representation that you develop is invariant with respect to many things. So first, it is invariance with respect to how it is physically implemented and how it is algorithmically implemented. So we know that, I mean, these three levels in the hierarchy of MAR are essentially, you can study this like independently one from the other, in the sense that we know, for example, some of the cognitive functions of humans, then they can be reproduced by ChatGPT, just if we change the algorithmic and physical level from the human brain to a machine. Okay, so this means that you can try to understand these functions irrespective of how they are physically implemented. Okay. Then, of course, I mean, you want abstract representation which are independent of a sensory modality. So you recognize your mom both if you see her or if you hear her voice, right? Or yeah, so a different. So you want say that an abstract representation essentially projects all these sensory modality on the same model. Okay, and you want to we want to understand what are the properties of this model. Okay. Then your abstract representation should be independent of symmetries. So you recognize objects irrespective of how they are portrayed in space, how they are rotated, how they are scaled, how they are translated. So there is a lot of what is called invariance in how we recognize objects. And this has been studied a lot in neuroscience, so how the brain has developed this capacity of developing invariant representation. And actually, what it has been found recently is that neural networks, so neural networks, of course, can say you can inbuild the symmetries into neural networks. This is what is done with convolutional neural networks. So for vision. No, in convolutional neural network, you take into account that data is invariant with respect to translation. So essentially, you can build this in the architecture. You can also help a network to learn invariances by augmenting the data, so translating the data, or say, so scaling the data, okay. But actually, what people have found is that neural networks learn, even simple neural networks, learn convolutions and all these symmetries just by their own. They don't need our help to learn symmetries, okay? And of course, I mean, so this is essentially what is a depiction, no? That, say, different objects, say, in shallow layers of neural network are entangled. The representation is entangled, but when you go deeper and deeper, then this representation get distinguished, and they can be distinguished by just a simple algorithm. Okay, and well, of course, then you want your representation is invariant with respect to context, or with respect to details which are not relevant. Okay, so so this means that if you want to understand what abstraction is, then this has to be independent of the data and or of the stimulus. Okay, and this is actually how, if you, this is actually how neuroscientists or say people studying abstraction in neural network have actually say address this question up to now, so that if you see that a neuron is responding to very abstract features, then you say, well, this neuron is doing something abstract. But could you say this without looking at what it is coding, without reference to the data? Okay, just from the statistical signatures of the activity of this neuron. Okay, so this is the question I want to focus on. Okay. Is this clear? Does this make sense? Okay, so in some sense, I would like to be able to put an electrode in the brain somewhere, record the activity, and being able to tell you how abstract is the representation in that area of the brain. Okay. Okay, so first, so now I want to argue that for a neural network, abstraction invariance is noise. Okay. So first of all, because well, invariance is related to independence. So it means, say, if there is an object which is invariant with respect to a certain transformation, then there is a variable that encodes this transformation, which is independent of the rest. Okay, and independence is a state of maximal entropy. So if you have two random variables, the state of maximal entropy of these two random variables when they are independent. Okay. So if you have this invariant invariance with respect to this coordinate, then this coordinate a priori can take any possible value. Okay, which means you will have a distribution of maximal entropy. Okay, because it can be, I mean, you don't know anything a priori about this variable. You have no, because it's an invariant. Okay, so your prior should be a prior state of maximal entropy. And state of maximal entropy is noise. Okay, so it's a state of maximal ignorance. Okay. So this means that invariances cannot be distinguished from noise. Again, I'm taking the perspective of a neuron of a variable which is deep inside this deep neural network. And for him, or for her, invariances are just as noise. Okay. Is it okay? So, or you can also say this so that invariances are that part of the data which has been understood or which has been coded in a particular part of the neural network. What you want to pass on is what has not yet been understood in terms of invariances. Okay, and that is what you could call meaning. Okay. Okay, so this is the picture that we got up to now. I hope we agree all with this picture. So as information processes from the input deep inside the neural network, you have that noise and invariances are pruned out, and what is transmitted is what we are really interested in, okay? And we want to characterize, okay? Are we all on the same page?
One question.
Yeah.
You said I can have a bias from the variable, right? That's still dependent from another one, which is sort of like, let's say I have a completely random variable that would maximize the entropy to be log 2 for that variable, but I can have bias in what I can say, oh, this only fires 80% of the time, but still independently from another variable. So is that also noise in this description or how?
Yeah, so let's say what I mean by noise is essentially anything which has a maximum entropy distribution. So let's say if you want a general recipe, let's say you have if you have, imagine your representation as this is a state of your machine deep inside one layer, this S. You are interested in this distribution of, because, I mean, if we stick to deep belief networks, then thing is very simple. We are not interested in dynamics. It's just a static representation, just the probability distribution of the internal states. Okay, so if you have an invariance, so if your space of you have some invariance, so you have some theta of S, which is just some collective variable which encodes some invariance. Okay. Then essentially the probability distribution, the marginal distribution of this value will be a distribution of maximal entropy. Okay, a distribution of maximal entropy is just say something which is proportional to an exponential of minus some constant like a coupling constant times some function of theta. Okay. And that is a distribution of maximal entities. So it's and then once you measure this thing, once you measure the value of this function here, you know everything. There is nothing else in this distribution. There is no other information. Okay. So what you have, I mean, is that once in one of these layers you learn that particular average of f, all the rest you can throw out. Okay? Okay, very good. Yeah.
This phenomenon of noise invariance going away, does it happen for generative networks as well, or is this like a thing that happens only in deep networks?
So, is this related with depth? This is what you're asking, or does it happen in more general neural networks?
I meant does it happen in like generative networks, like let's say,
Yeah.
I want to see an image come back, or
Yeah.
like DALL-E or ChatGPT.
Yeah.
Because if it's a generative network, then the symmetry also has to be present in the output.
Yes, exactly. Yes. So a particular symmetry, so if a symmetry is detected here, at this layer, it means that it is present in all the previous layers, but its absence is absent out after that. Okay, so this is what I mean by once you detect an invariance, then it's like noise, you throw it away.
Okay.
Okay. Yeah.
My question. So, in your definition of invariance, it seemed as if you were talking about multiple random variables, but actually you're really talking about one random variable. Because
No,
you define it in terms of maximum.
No, actually, you can understand how many random variables. I'm coming to that. So how many random variables? Just look at the entropy of the representation.
But I guess I don't quite understand your definition though. Independence, statistical independence, involves more than one event, or more than one random variable.
Yeah.
And entropy is a feature of the random variable.
Yeah. Yes. So essentially, you have your network. Here you have your data. Your data is a very high dimensional vector.
Sure.
So, and here your internal representation is a vector of n binary variables in this case. Okay. So you can think what is happening here. I'm going to get to this. It's essentially compression. Okay.
No, I think that this is not what I'm talking about.
No, wait. So it's compression. So the entropy of the data is very large, and the entropy of these variables is low. And as you go deep, you compress. Now, essentially, this in this binary world, this entropy gives you essentially a measure of the logarithm of the number of random variables, right? Okay. So that when you compress, it's like eliminating random variables.
I mean, sure, you're making it more deterministic, so you're, reducing.
No, it's still stochastic, but you are compressing it. Yeah. Yeah.
I guess my question is, I don't understand how this is related to statistical independence. What does it happen to independence?
Well, statistical independence is a state where, so if these variables are independent, then this entropy is maximal. So, I mean, if you have two random variables, x and y, the joint distribution is the sum of them minus the mutual information, right?
Yeah.
So the maximum is when x is 0.
So you're really talking about mutual information.
Yeah. I'm talking about independence, and independence is precisely defined when this is 0, right?
Okay.
Yeah. So I'm talking in very general terms. I mean,
No, it's just a bit confusing because entropy really refers to a single random variable. But what you're really talking about is mutual information.
Yeah, I'm talking at the entropy of this whole set of variables and all of the data, yeah, of vector of random variables. Yes. Yeah. Okay. So I'm going slow, but I care about not missing anyone. So because I think this is very nice. Okay, so the next step is that meaning. I mean, we have a quantitative measure for meaning, which is relevance. Okay, and if you have followed me up to this point, you will understand that whatever is understood has a very good statistical model, okay, like this one. And whatever is not understood has a model which is still fluctuating, which is, well, there is uncertainty, okay? So relevance, measure of relevance or of meaning is how much the model fluctuates. What is the entropy of the models? And the nice thing is that you can measure this on the data by measuring the entropy of the frequency, because the frequency is an estimate of the model, of the probability. Okay. So this is what we call the relevance. Okay. And we have studied this thing of relevance for quite some time now. And so you can portray all representation in this two-dimensional space. One is a compression axis. So this is just the entropy of the internal of a data set. Just the usual minus PS log PS sum over S. Okay. And relevance instead is the entropy of the frequency distribution, of the distribution of how many times you see a particular state in your data set. Okay, and this is a measure of how uncertain your representation is about the model of the data. Okay. Okay, so what we did was to study this thing, and so you see this black line. It tells you that there is a maximal value of the relevance at a given value of compression, and this scale, we call it a resolution. Okay, sorry. What did I do? I did something wrong. Maybe I should do like this. No. Oh. So what's yeah. So maybe I stop sharing and then start sharing again. Okay, so now, yes, so as I was telling you, oh, great, thank you. Okay, so this is the maximal value that it can take. And these are the value that are achieved by representation in different systems. So, for example, here you see, you can take, I mean, this applies also to language, no? And you can compute these things for translations of the Bible, and you will see, so you will see that that they fall exactly on this maximum line, and this maximum line, this is what we call the representation that maximize this relevance is what we call maximal informative representation, and they have this feature of being naturally critical in the sense of statistical criticality. That is, the frequency distribution is power law, and this is simple. But also, if you look at the internal layers of a deep belief network, then you also find that once you train your neural network on very rich data, then you also get a representation which are maximally informative, or say maximize this relevance. And you don't do that if your data is completely useless, is noise. If your data is noise, essentially you don't get very high value of this relevance. Now, this is an axis of compression, and it tells you, and both axes are measured in bits. So this axis tells you that when you learn, you go in this direction, you compress. So when you compress by 1 bit, if the slope of this line is larger than, say, 1 in absolute term, it means that you gain more in relevance than what you compress. Okay, it means that the data that you have been compressing give you more information about the model. Okay, so there is one particular point, which is this one, beyond which instead things change. So you compress by 1 bit and you learn less than 1 bit on your model. So this point is a special one, which marks this transition between, say, what you would call undersampling regimes, so a regime or representation which are still noisy, and say, a lossy compressed regime. And it's interesting, and most of interesting representation are exactly on this point, and this point is what is characterized by zip flow. Okay, so I could go on and talk for 2 hours about relevance and all the nice things that they allow you to really extract interesting information from data, but I want to focus on abstraction. So if you want, I can give another lecture on this. But the key point is that now you have an absolute quantitative measure of meaning, of relevance, which is not related to what you are learning or how you are learning, which is just related to what is your representation. And then you can start asking interesting questions.
So, I understand that. So relevance is how much you learn when you compress it?
Yeah, it's how much you learn about the generative model, the model that has generated the data. Okay.
How do you calculate this relevance?
Okay, so it's very easy. So it's trivial essentially. So imagine that you have your data set. You have a data set, okay, which is n observations of the state of a system. Okay. Okay. Then you compute the frequency. So how many times you see how many times you see a particular state? Okay. Then this gives you an estimate of what is the frequency. Okay. Okay. And then you want to understand what is the entropy of this object, which is essentially the entropy of the frequency. Because you estimate this from the data, well, this is the empirical estimate of the entropy. So it's just minus. So you have to compute what is the probability that in the data you find a point. You find a point which is observed k times. Okay, and this is just k times the number of objects that you see k times divided by n. And then you just do Shannon. So this is just k, no, k.
So
Okay.
you group together all states that are observed the same number of times.
Exactly. And why you do that? Because if they are seen the same number of times, the probability distribution is flat, which is a state of maximal entropy. So the data does not allow you to, I mean, the frequency does not allow you to distinguish between these two states. Okay. So instead, if you have two states which are seen with very different frequency, this cannot be noise.
Whereas the compression on the x-axis does distinguish.
The compression on the x-axis
That's its age of
instead is just the same thing we want, but just with the P of S, which is just K over N. Okay. And okay, so I think I should go ahead. Is it okay?
The plot is okay, and then where it comes the relevance from this rule,
Sorry?
then the relevance comes from.
So this is the relevance. And this is what we call the resolution. Okay.
So are you able to tell us give us a concrete example of these things? Like you're using these words, meaning, what is, if I'm training a neural network to identify pictures of a cat, what is the meaning?
Yeah.
Can you give a concrete thing? Yeah.
No, yes, so that's exactly the problem. I mean, we are talking about all these things without pinning them down to a quantitative object or a quantitative. It's like, I don't know, in 17th century, people were talking about heat or without having a notion of entropy. Okay, or what heat really is. I mean, people were talking at ether. I mean, so the idea of this relevance is that, okay, so it is what it is, but it allows you to ask this question.
Yeah, I'm just asking what is actually giving us. I mean, concretely, if you're, training something to identify a picture of.
So let's say this is telling you. Well, it's not telling you exactly this, but this notion characterizes what type of information is being transmitted inside this neural network. Okay, because it's a state of maximal relevance. Okay, this is what is maximized. This is what is relevant for this machine. Okay, and so this must be related to meaning. Okay. Okay.
Meaning, the closer you the straight line. I mean, meaning is a big word, yeah, but
yeah.
if you're saying you identified some relevant information in this
No,
system,
I'm just saying. Okay, so my argument is this, I'm just my word is this. Okay, and I'm thinking what is relevant, what is meaning for the internal representation of a neural network.
What is
Okay.
meaningful? Yeah. Okay.
What is meaning for this machine? Okay. And I'm saying, well, meaning it's essentially measured by this relevance. Okay. Of course, then if you say what is meaning for us, I mean, we are talking about a system which is much more complex than this, and I don't have a question, but in this world, I can argue, that I may convince you that there is a quantitative answer to this.
You understood then checking this plot, the closer to the straight line, the closer to an uniform distribution and the large, and the further, then you have more relevance, or how does it works?
No, well, this is just this is a different learning regime. So this is the classical statistics regime, where essentially you have a lot of data. Your model is finite, and you take the limit when the data goes to infinity. This is the classical regime. Okay. Now, all this description and actually what neural networks, I mean, are great at doing also is essentially they are extracting information in this regime. And this is also the regime which is relevant for living systems. I mean, a bacteria doesn't want to compute the concentration of antibiotics to 5 sigma before take some measure to escape, right? So survival really depends on early detection, on really forming an idea of what the state of the environment is without taking an infinite amount of data, right? So, okay. Okay.
Question.
Oh, yeah.
Sorry. So your notion of relevance is very empirical in nature.
This is the empirical part. You can also measure it. You can also define it for a model.
Okay, so it could be used in inference as well.
Yes. And this is what I'm going to do. But the idea is the same, that if you want to have a broad distribution of frequency, then as you talk to models, you want to have a broad distribution of energy, if you want, broad distribution of coding costs. Okay, and this is the same, again, this is all explaining this. Okay, and this is essentially what this maximum entropy principle tells you, that if you maximize the entropy, then the degeneracy of what you may call energy levels, but they are actually coding costs. So it's actually, because we are taking temperature being equal to 1, should essentially be exponential. This gives a precise prescription of how an optimal representation should be. So it's optimal in the sense that you are using bits in an optimal way. Okay, and this can be understood easily. So if you have an object which has a certain probability p, then the number of bits that you need to describe it is minus log of p. Okay. Now, how many objects can you describe with that many bits? It's just minus log of p, because you have because you have that many bits, and both of them can be plus or minus 1. Okay, and this means that the number of bits, so the number of yes, the number of bits that you use should be equal to the log of the number of objects that you can describe. Okay, and this means that the entropy essentially should be linear with the energy or things like that. Essentially, if you ask yourself, well, let's think about a model of binary variables that can be either 0 or 1, such that you don't want to assume anything about so you want to have a model that says, okay, where these variables code for features, and these features are organized on a scale of detail, from more detailed features to less detailed features. And you want to say that you want a model such that if you have a certain feature here, then any lower order feature can be there or not with the same probability. You don't want to be, but then all other features, yeah, so you want to have this property, and then you want to have this property, and the only model that does that is the model which has this Hamiltonian, where you take a configuration, you take the index of the largest spin, which is up, and then that is your energy. Okay, and it's called it's a spin system. If you want, you can build it as a spin system, and you can do all statistical mechanics. You can see there is a phase transition. You can see it's a very interesting simple model. But the thing is that it's the only representation that encodes these two principles: maximal relevance, essentially maximal a priori ignorance of what you're going to learn, essentially on the features space. Okay, so this, believe me, okay, this is the only possible. Okay, so now you can start asking questions, so you can understand, say, for example, how does learning difference from learning? How does understanding differs from learning? And let me explain what I mean. So for learning, you can take this model here, which is essentially a restricted Boltzmann machine. So it's a machine that works very well. Here you can see how it behaves also on these digits. And this is the model. So the main thing about this model is that it's meant to be simple so that you can do calculations. But you see that the joint distribution depends both on the visible and the hidden layer with this bilinear form, in a very strange way, because essentially once you condition on the visible variables, the hidden variables are independent. So this tells you that the type of information that you pass through, it's only in single variable statistics, only in averages. Okay, so this is all the rest, all the other statistical patterns are not informative. Okay, and then essentially the way you train is just to maximize the likelihood of the data, and but then what you can do is to look at what is the internal representation, what is the distribution of the hidden layer. Okay, and what you see is that essentially learning in this machine is a little bit like this. So you have your model, and during training, you build your model, internal representation, and you learn the weights at the same time. Okay, so it's like you build your library while putting books in it, while fitting it, okay? And you can see that the model, indeed the model changes a lot during training, and that the distribution of energy levels or coding costs really gets broader and broader during training, okay? Now, instead, if you think about understanding, well, understanding in a simple mind like mine is like projecting data on an already existing representation And now that we have the hierarchical feature model, we know in what representation we should project, okay? Because otherwise, if you have no clue of what are the properties of a good internal representation, then you cannot do this, okay? And so we take a machine where essentially the joint distribution is just a projection from the hidden state to the visible state times the internal representation, which is fixed. Now, the internal representation is not learned. What you learn are just the weights, okay? So it's like you have your library, and then you put books inside. Okay, is this clear? Does this make sense? Okay, and somehow what this is telling you is that you are essentially given the internal representation, you want your features, your data to be as independent as possible. So which means that you want that your visible variable inherit all the statistical dependencies from the hidden layer, from this optimum organization of features. Okay. Okay, so I think really getting late. How much time do I have? 5 minutes. Okay, so I'm essentially done. So what you learn is that this way of learning is very flexible, in the sense that, say, when you learn something, then you can think, okay, so I'll add some more data. And you don't want that the new data that you add screws up what you have already learned. Okay, this does not happen in a Sitter-Bonsa machine. Okay, so instead it happens here. So there are continuity properties of learning that you want to be there. You want to be. I mean, if you want to augment the capacity of your representation by adding one new spin, then you don't want this to screw up everything else. If you want to, the other thing that you want to do is you want to summarize. You want to change the entropy of the data, of the internal representation, without having to relearn everything. And this you can do with these models because you just do large deviation theory in the hidden layer, and it's just changing one parameter, okay? And it can also do interesting things. So, for example, it can imagine that, there could be pants with sleeves, and it could draw association between things that you learn in different contexts, which is what we also do, okay? So this is an example of relation between digits and emotions, like personality traits. And okay, so okay, so now what I want to go back is instead relate abstraction and depth. So try to and the general question is this. I mean, as I go deeper into a deep belief network, does my representation get closer to this model or not? Okay, and this is actually what we find. That what we do is take the Kuba-Kleiber divergence between the data and this model, the hierarchical feature model. And what you show is that essentially, if you go deep, this DKL decreases. So you are approaching, your internal representation is approaching this abstract representation. Also, what you're seeing is that this DKL also behaves as expected or measure of abstraction, in the sense that you expect that the wider the domain of the data, the more abstract should be your representation, right? So if I learn a data set which has a very small variation, then my yeah, so my model will not be very general, okay? If instead I force a neural network to learn a data with a large variation, then the model should be more abstract. You should describe very different things. So if you want a model that describes, I don't know, only digits, and in particular, this is the case where you want to describe this orange line, when you want to describe a data set which is made of just digits, so 2 digits, the digit 2, transformed in many ways, okay? And then you see that what the network will do is to learn a good model of the digit 2. That's it. And it will not get close to this abstract representation, okay? If instead you mix all the digits, then your internal representation gets more abstract. And if you mix digits with letters, it gets even a little bit more abstract. Okay? Does this make sense?
Sorry, on vertical axis, there's this tool flavor.
DKL is
DKL
the distance between the data and this hierarchical Fisher model, which is like a candidate for an abstract representation.
And the axis, the model with more layers, or?
And the horizontal axis is the layer. So one is the shallow layer, and here you go deep.
So you make a model deeper and deeper.
No, the model, I trained a model with 10 layers. And actually, I didn't tell you anything about the model, but it's a DBN, so it's a stack of Aristotle Potter machines, which are then one after the other. But I trained this network with a given data set, okay? And then I look at what is the probability distribution of the different layers. And I compare this probability distribution with this model. I look at how distant they are in terms of DKL distance. Okay? So this is the picture, no? So what I want to understand is whether when I go deep, my representation goes close to an abstract model, which is this HFM.
Am I correct that for Muni's data set, your abstract model is like you learn that there are 10 different digits and the rest is noise or something like that?
No, actually, I mean, the data which is there in MNIST is whatever it is. I mean, say, for example, there are these people who have found that there are some features that neural network learn that actually are meaningless for us, and but for them these features are as important as other features that are important for us. So what you do with when you do supervised learning is that you train this network, then to the last layer you attach an output layer where you tell to this guy what is important for you. And this guy will say, then pick out of this will skew the representation, the probability distribution towards what is important for you, which are the labels, okay? But here I'm just describing unsupervised learning, so okay?
So your learning objective is to
maximum likelihood.
maximum answer.
To get this embedded representation of the data, you are using autoencoders or?
No, I mean, the setup is very simple. This is a deep belief network, and which is just a stack of receiver machines. It has a certain shape. I'm not going into the detail because these are not important. I want to discuss features which are, say, sort of general. So, okay, so this DKL behaves as you expect, and also say you can use this model essentially as a knife to say, okay, so now look at my representation. I want to say part of it is noise or is something which has a flat distribution, and part of it is maximally relevant. And you can look at where the cut is, and you can see that as you go deep, this cut essentially goes to zero in the sense that everything is important, okay, is meaningful, okay. And so this is instead the DKL of the data with the best pairwise model, best easy model with up to pairwise interactions. Okay. Now, why do we do this? Because the easy model is a very complex model. The pairwise models are very complex models. So in information theoretic sense, this means that they are able to describe a wide variety of data sets. Indeed, the pairwise model has been used to model neurons in the brain, US Supreme Court behavior, the immune system. You can use it for everything, essentially. So instead, a very simple model is a model that describes only one data set and does not describe. You cannot tweak the parameters to describe something else. So it's a model with a rich structure, okay, which is not flexible, okay. And okay, so this, so you see that if you measure the DKL, you find that the DKL of shallow layers, so the shallow layers are very close to be pairwise models. In the shallow layers are very close to pairwise models. And as you go deep, you start instead, you need higher order interactions. So this, you have to go away from pairwise interactions to really describe this meaning. I mean, this is what this suggests. And so you go from a sort of a generic representation to a very abstract one, okay? And this is the last thing I want to tell you is that also plasticity increases with depth. Okay, so what you can do is you take your network, you train it on a given data set, then you change the data set and you retrain. And then you see how much the weights change. What is the distance, how distant are the weights when you train the second data set from the first. And you see that essentially the shallow layers do not change much, whereas deep layers change a lot. Okay, so this tells you where is the information. Okay, so the way I want to put it is, imagine that you learn images and then you want to understand where is the cat, where is this information about this guy is the cat, and these images are so in shallow layers. This means that if the weights do not change much, they do not depend on the data. It means that information is really in the activation, in the activity of these neurons. Okay, whereas in deep layers, the representation becomes more and more abstract, independent of the data, and so the information is in the weights. Okay, so this in shallow layer, the way in which you learn is similar to restricted Boltzmann machines. In deep layers, the way in which you learn is similar to Hopfield models. For those who know what a Hopfield model is a model where the memories are for storage of memory, and memories are in the weights, in the couplings. Okay. Okay, so very good. So by the way, this is also what happens in our visual hierarchy. So your retina is hardwired at birth. V1, the primary visual cortex, gets essentially frozen after a few months from birth, but you keep on plasticity in higher cortical areas, and so okay. Okay, so this is we studied also how information percolates, but I think I went already quite. So it's very late. So this is my summary. So just to summarize, what I try to tell you is that if you restrict yourself to very simple systems like deep belief networks, you can get a picture of what is going on and how this, what you can really look inside and ask yourself, what is abstraction, what is going on, what is learning, and say, and then what you see is that I mean, the point I want to make is that as you go deep, you go from a very generic representation, which is good for any type of data, and this is the success of transfer learning, right? So transfer learning means you can use a neural network trained on a particular data set on another data set by just retraining the output layer, okay? So this is because your internal representation in shadow layers is very generic, okay? So you go from a generic to an abstract representation, which is data independent. You go from a complex model, like a pairwise model, to a very simple model, this hierarchical Fisher model. You can compute the complexity, and it only grows as log the number of spins. It's very which is actually interesting, but okay, so it's another point. You go from a situation where your network is essentially hardwired to a situation where instead your network is very flexible and plastic. Okay. Okay, that's more or less what I wanted to tell you.
Thanks a lot for this talk. We had a lot of discussions already. Maybe we can have a few more questions.
If we return to the very beginning, as far as I understood, you present a framework that allows to like define what is abstraction in a purely unsupervised way. And you define abstraction, the procedure of abstraction as removing noise. So let us consider a very simple model. Let us assume that my data basically contains two variables, and these variables are just independent random variables. And then we can say that the first variable is our meaning, in a sense, and then the second is a noise because it is independent from the first. Or we can do it vice versa. We can say that the second variable is something meaningful, and the first is a noise.
Yes.
So how do we distinguish between these two?
By the by the relevance, if you want. So if you have the marginal distribution of one of these two variables is essentially distribution of maximal entropy, that is not interesting. That is the same information theoretic characterization as noise. If you have a distribution which is not of maximum, which is as far away as possible from a distribution of maximal entropy, then that is interesting. And that is, I mean, that is so evident. I mean, learning, I mean, so we understand what is interesting before understanding why it is interesting. And like living systems are like this, you understand why something is interesting just from the statistical features, not in any unsupervised way, because you know, because you, I mean, because you are, well, you already have a model, or I mean, and also, I mean, this is another deep question of why life evolved. Learning systems, so systems that are interested in models which have this distribution which are away from maximum entropy, and there is a reason for that, because distribution of maximal entropy characterize inert matter. This is statistical mechanics. Statistical mechanics is maximum entropy. So a system like this glass is described by Boltzmann distribution maximal entropy, etc. And this means that this glass could not care less about the environment. Okay, because it's a distribution of maximal ignorance. Okay, living systems are not like this. They want to understand, and if you have, so if you want to understand, if you are sensing some information or some signal which is out of equilibrium, it means that you can do something with it. It's energy, because it's in a non-equilibrium state. It's a non-equilibrium state. It means that it has been driven by something out of equilibrium. And you can use this to make stuff. So I mean, all these things are related one to the other. No, so does this make sense? Yeah. So this thing of trying to understand, say, the energetic part, I mean, how this relates to the physical, okay, so why, so it's another field which is remarkably interesting, which is related to statistical, stochastic thermodynamics, information thermodynamics, etc., which is now, these are all questions that you can start thinking about. Yes. So